It allows for two things. One is sparse connections, we will see what those are later as we progress, as well as parameter sharing. And because the images are used as input, these two concepts are possible. Basically, it is possible to have sparse connections as well as weight sharing of weights between the output neurons in a layer. CNNs in the recent past, and of course especially since deep learning has taken off, has found huge applications basically in image recognition, object detection, localization, semantic segmentation and medical image analysis. These are some of the areas where CNNs have shown extremely good performance on many benchmark problems and are now being tried out for many commercial applications. So, for instance, let us look at this many commercial applications. So, this is an image from the wild. It is an image showing a rural scene somewhere, and if this image is given as input to the Google Cloud's vision program, it is freely available, you can also try it out. Then it automatically describes the image as saying it is a herd with a 91% probability that it has goats in them, and there is actually a herder in there. It also identifies grass, it also says livestock in this case, okay, and that this guy is, the man in the picture is actually herding. So, this level of detail is possible, this is the level of performance is possible with current CNNs. Here is an output from another CNN from Silver Pond. It is an object detector. So, it is able to identify the man in the picture as well as the goat. However, it does label it wrongly as I think a horse. Okay. So, it is able to localize as well as identify the objects. Okay. It is a typical application that you would do with a in computer vision. That is what you would, these are typical application in computer vision, and it is not too hard to think of some very what everybody now talking about the self-driving cars. You can see that if you have a vision system in a self-driving car, you can, if it performs well, it can identify obstacles, zebra crossing, application in computer vision. CNNs also find applications in image analysis, and in this case we are looking specifically at medical image analysis. So, if you look at this image here on the left, it is an image of a brain, MR image of the brain, it has been pre-processed to some extent. So, you can see some abnormalities here and there, okay, and what you see on the right what you see on the right here are basically the pixel labeling tasks done by a CNN, where it correctly identifies, or to fairly correctly identifies regions that appear as classes within. There is a huge advantage in terms of, so a typical image, medical image, and huge support for radiologists who database. Now, this ImageNet challenge, visual recognition challenge, has been going on for quite a few years now. Basically, the challenge organizers make available to you millions of images drawn from the wild, from the internet, and labeled by experts as belonging to one of 1000 categories. And when given an input image from a test set, you again containing several hundreds of thousands of So, this is actually image of a side wire, and this is again a shipwreck. I actually do not know what that is, but anyway. So, and these are some of the predictions made by a typical network which is trained on the database. The challenge is that the correct class should be among the top 5 predictions of many other. It itself is a deep CNNs which outperform this. So, for instance, if you look at neural networks, accuracy if you see is pretty impressive. It is almost about 95 to 96%, which is approaching human top 5 accuracy. Okay. We will see what these mean. The parameters of the network, the depth we will see later what it means, but parameters of the network are basically the number of weights in the network. They range from a million to 140 million. Okay. So, over time people have started off with a very large number of weights, and over time the networks have trimmed down. They have gone deeper, but they have managed also to reduce the number of parameters in the network, and also improve the top 5 accuracy. Okay. So, before we move on to what CNNs do and how to build your own CNN, let us look at how images are parameterized. Okay. So, we saw earlier that CNNs take images as input. So, what does it mean? So, you know that for an artificial neural network, the input is usually a vector of values or labels or some categorical label if you want. But as far as a CNN is concerned, a convolutional neural network is concerned, the image is an input. So, there are different types of images, grayscale as well as RGB. So, what do you mean by saying a image as input? So, if you take a grayscale image, here is a digit image of a digit 8. So, you can think of the image as being made up of, so this is actually a matrix. So, this is actually a matrix. It is a 2D matrix, okay. It is a 2D matrix, and the image is made up of pixels, with each pixel having a particular numerical value. So, this whole image is actually a 2D matrix, and if you can think of it as like a grid, I can draw some crude grid like structures here, and point there is a numerical value associated with it. So, that is the pixel value. So, in a typical image, for instance, the images that you take with your camera, the values of the pixels range from 0 to 255. They are referred to as 8-bit images. Right. And the dimensionality of the input is basically the size of your 2D matrix. So, if you might have nx pixels on the x axis and ny pixels on the y axis. So, your image input is of size nx times ny. This is your input to a network. If you want to think of it in terms of an artificial neural network, your regular artificial neural network, you have an input vector of size nx times ny. To give an example, MNIST database has digits, the images of digits which are of size 28 by 28 pixels. By 28 pixels. Digits, the images of digits which are of size 28 by 28 pixels. So, that means it is a force vector of size 484. Okay. So, as far as grayscale images is concerned, you can think of them as a 2D matrix of dimension nx cross ny depending on how many pixels are there along the x or the y axis. And if you want to think in terms of a regular INN, the size of your input is basically the total number of pixels in the image. Okay. Now, images, by images we also mean RGB images. In that case, let us take a color. RGB images are basically your typical color images. If you take an RGB image, we can extract the individual channels in RGB image. So, an RGB image consists of 3 channels RG and B. Each channel itself is an image. So, and the pixel values in each of the channels range from 0 to 255. So, what you get as an RGB, as visualized as an RGB image is basically the combination of these RGB pixel values. So, if you want to give, if you want to give a CNN, an RGB image as as input, which means that, so you have for every image nx ny nx times ny pixels as input. However, there are also three channels, as they are called, as the terminology typically used in CNNs. So, your input is basically NX, rasterize the image and make it into a vector of size NX times NY times 3. So, the CNN basically takes, if you can generalize, CNN basically takes a volume as input. By volume I mean that you have a pixel array of given size NX and Y. However, there can be multiple such arrays which gives rise to a volume. CNN takes as volume as input, class label based on your objective function. So, since we can rasterize these images, so we can read out these pixel values one at a time and form a vector, and then why not we just go ahead and use a regular artificial neural network. Now, if these images are small, let us say if you have a 32 by 32 image, or let us say 30 by 30 images for the sake of calculation. So, you have a 30 times 30 image, even there are 3 channels. Okay. So, so this is basically 2000. 1700 input neurons for a regular ANN. Okay. So, you will have about 2700 neurons. However, most regular size images are of the order of 220 or 256 times 256, and if you have 3 channels. So, this is already of the order of 10 raised to 4 and 10 raised to 5 neurons. Okay. So, which means that if you are taking, let us say if you want to get a hidden layer of 1000 neurons, which will give rise to 10 raised to 8 weights. This is a very conservative estimate, because sometimes the images are as large as 1000 by 1000 or 512 by 512, especially medical images are quite large. So, as the size of your input images increase, ANNs do not scale very well. So, they are unable to handle such. The number of weights, or there is the explosion in the number of weights that has to be estimated. We use and that means that proportionally a large number of data points are required. Another aspect of why we should not use ANN is because ANNs because ANN takes as input a vector. So, which means that even if you are given an image, we have to vectorize it by rasterizing it, and in that process we will lose the spatial structure of the data. Okay. So, images have spatial structure. So, which is what we want to exploit by using a CNN, and in the process we also, as we saw earlier, exploit 2 more things. We get a sparsely connected network, which means that there won't be as many weights as in an artificial neural network. In addition, there is also parameter sharing, which again reduces the number of weights, and parameter sharing which in turn enables that us to exploit the local connectivity of a neural network. Sorry, the parameter sharing enables us to exploit the local connectivity in an image. So, what does a CNN consist of? Okay. CNNs, like ANNs, consist of sequence of hidden layers, but these hidden layers are basically convolutions or pooling. Okay. So, we will see what these are in later slides, but it is a alternation of convolution and pooling layers, followed by a series of fully connected layers, just like in artificial neural network. leading to a classification layer. This is a typical structure of a convolutional neural network. Now, why do we have this kind of structure? What is this convolution doing here? What does it mean? What does convolution accomplish? We will examine that. Okay. Before we go there, we will also look at, just to summarize, CNNs take as input, as we saw earlier, images, but these images can be can have multi channels. So, a simple example being a RGB image which has 3 channels. So, they take as input a volume, and in each layer in a CNN outputs a volume, irrespective of whether it is a convolution or a pooling layer. Okay. This is different from contrast to ANNs, where the output is of every layer is basically another vector of neurons. So, just to summarize again in visual form, a convolution layer takes us, so in this case the input is an RGB image, and we won't look at what the operations are right now, but the output from a layer is basically a volume here, where if you you can slice the volume this way, okay, then have multiple outputs or multiple 2D outputs. Each of these is a 2D map. Each of these 2D output is often referred to as a feature map or an activation map. Okay. So, the number of output feature maps or the activation maps is entirely within our control. We will see how that can be defined. Okay. And the size, the 2D map, the size of the 2D map, the nx, ny coordinates of 2D map again is determined by the operations we perform. Similarly, even for a single input channel, so this is for 3 input channel. So, irrespective of the size, number of channels in your input, you can have multiple channels in your output. This is true of every layer. So, for instance, if you take this layer, this can again undergo another convolution leading to even more higher number of activation maps being output. We will see that in some popular CNN architectures later on. So, why convolutions? Why what do these convolutions accomplish? What are they inspired by? We will look at what exactly convolutions do, but before that. So, in the 1960s, Hubel and his colleagues did a series of experiments measuring the activations or signals from neurons in the primary visual cortex of cats. Okay. We will not go into exactly how they did the experiments, but these are biologists, they knew what they were doing. They eventually won the Nobel Prize for this work. And they found out that in the primary visual cortex, the primary visual cortex in turn, as we see later, will take its input from the retina. Retina is where what we see is projected. So, our eyes, the lens of our eye projects whatever we see onto the retina. So, the primary visual cortex and the signal from the retina goes to the primary visual cortex. So, the primary visual cortex, they found out, have 2 types of cells, neuronal cells. The simple cells, the simple cells of course get their signals from the rods and cones in the retina, and these simple cells respond to edges. So, they had very good response to edges of different orientations, and it was a linear response. Okay. And then there are other type of cells called complex cells which seem to take input from the simple cells. So, a linear combination of input from the simple cells and had a nonlinear response, and one aspect of which was that it was insensitive to translations. So, you can move an edge across the eye or have a project an edge on the retina of the eye and move it across the retina, but the output from a complex cell would be the same. That is what it means. So, they concluded that the visual cortex had these 2 type of cells, and this behavior they characterized. Okay. So, this was the inspiration for. So, if you want to look at it, so this let us say is your eyeball and this is your retina right here. Take as in input signals from a particular region. This is a region, a small region here. For this cell. So, this is called the receptive field of that particular cell or group of cells, receptive field. Okay. So, what it does is it does a linear combination of the signals from the receptive field and provides an output. Okay. Similarly, there are a bunch of these simple cells, each has its own receptive field in the retina of the eye, and they in turn provide an output, and this complex cell takes a weighted combination of these inputs and provides an output, and it is non-linear output, okay, from these cells. Okay. So, this is the inspiration behind CNNs. So, they try to mimic this vision system. This is of course the general wisdom that goes around, but of course there is not a very good understanding. There is a lot of progress on this field on how vision system works, but this is a very simplified, should I say, cartoon version. In my case, that is what I have done here, cartoon version of how the vision system works. So, another way of looking at this is, why do you use convolution, is that if you go back to signal processing or conventional image processing techniques, it is well known that if you have an image, we can define filters or what you call kernels okay. You can have a filter or filter kernels as they are called, which if you operate on an image should be able to extract different features from it. So, in this case I have shown a very simple kernel, say it is a one row 2 column, is a 1 cross 2 filter kernel. So, all you have to do is superimpose it on the image. So, this is 1 and minus 1, multiply with the underlying pixel values and add them. You can see that by applying this filter kernel and of course translate and do the same thing everywhere. Okay. So, if you do that all across the image, then you will get the edge map. Now, it is possible to construct by hand different filters like these, which will highlight edges at different orientations. So, there are multitude of filters. So, for instance, there are Sobel filters or Pruitt filters and so on, which have been already been there for it is well known in traditional image processing literature, that these filters can be used to highlight edges in an image, which is very similar to what we saw with how the simple cells work. Is basically we move this kernel. So, the receptive field for this kernel is about 1 cross 2. Okay. So, we can make 3 cross 3 Sobel Bell filter. So, the receptive field for that filter is a 3 cross 3 region in the image. Let us say if we define a 3 cross 3 filter, then this will be the receptive field of the filter. Enough filters, then we will get a variety of edge maps. This is just one layer. First, we can call this the first convolution layer, and then we do more combinations of those edge maps to get maybe higher order descriptions of your image. Okay. So, what these kernels, filter kernels exploit is that the edges in an image are similar everywhere. So, for instance, if you have a vertical edge somewhere in an image in one region of the image, let us say there is a edge, in this case there is a edge here, I have a similar edge here too. Their orientations are different, right. So, you can, or I can have an edge here which is very similar to the edge that I just pointed out right now. This edge here and this edge here are the same, very similar, right. So, if I define a filter that picks out an edge at that angle, let us say that is a 45-degree edge, then I can use it all over the picture to highlight that particular edge. Okay. So, this is what this parameter sharing is all about, in the sense that for identifying a particular feature, I do not need to define a new filter for every region in the image. It is the same filter that I can apply for, and wherever there is a edge at this particular angle, that filter will pick it up. Okay. Okay. This is another way of looking at a convolutional neural network. Okay. So, what does convolution accomplish? So, like we saw, the convolutional neural network, same structure as artificial neural network. There is an input layer followed by a sequence of hidden layers, and then there is output. Now, the output of any hidden layer, and for in general, you can think of an input as also as a layer in the network. So, the output of every layer, the neuron in the output of every layer is connected to a small neighborhood in the input. Okay, that's what the convolutional kernel accomplishes. The filter kernel we saw in the last slide, that's what it accomplishes. And the connection is through a weight matrix, which we call the filter or a kernel. Okay. For every convolution layer, we can just define multiple filter kernels. And the way it works is that we move the filter kernel around the image, and at every region and at every position that we move it around to, we multiply with the underlying pixel values and add them up. Okay, it is a sum of products, and so which gives rise to a corresponding output. So that since we can define multiple filters in every layer, we can stack the outputs of each of the filters obtained by applying each of the filters to the input and giving rise to another volume of hidden neurons. So, let us just neurons. How a typical convolution works. So, let us just look at how a typical convolution works. So, what we see on the left here is your just a toy image, you can call it, it is a a 5 by 5 image, and on the right is your 3 by 3 convolutional kernel. So, let us just look at how a typical toy image, you can call it, it is a 5 by 5 image, and on the right is your 3 by 3 convolutional kernel. Okay. So, how does one actually perform the convolution? That is what we are going to see. It is very simple. All you have to do is superimpose the convolutional kernel starting at some point at the top left part of the image. You can start from anywhere, typically top left part of the image, multiply So, this will be 1 cross 1 times 1 plus 0 times 1 plus 2 times 0 plus 1 times 1 plus 2 times 1, so on and so forth, and you multiply and you add. So, it is a sum of products of the corresponding elements. The element that, which means that, so you, the corresponding elements in the image with the filter weights. So, that gives rise to one element in your output feature map. So, next step is to slide the kernel to the right or by one pixel and perform a similar operation. We can keep doing that. Or by one pixel and perform of the image. So, now if you go any further, then the filter will not fit completely in the image. So, we stop there and then we move 1 pixel down and then continue to do so, and at every point we place the kernel, we multiply with the underlying pixel values, add, and then obtain the output, corresponding output there. So, as we move through, we see that at every position we perform the same operation, and again once again as you come here, if you go down any further, if you move the shift the filter down any further, then it won't completely, it won't be fit fit inside the image. So, we stop right there. So, in general, if you have an image or input of size nx times ny and your filter kernel is of size fx or fy, your output size would be nx minus fx plus 1 and ny minus fy plus 1. This is a basic output. So, you see that as you do the convolution, the size output size keeps decreasing. Okay, this will happen. There is a way to stop that. We will see how to. How that is done in more systematic way, but this is typically what happens when you do convolutions. So, at every convolution layer you will define a multitude of these filters. So, when I say define, you really do not know. So, because these are the weights, like these are similar, these are the equivalent of the weights in your artificial neural network. So, that is what we typically estimate in artificial neural network, the weights of the network, by optimizing an objective function. In this case, we will determine the members of the filter kernel again by optimizing a suitable objective function. So, at every layer given an input, we can define many such filter kernels. So, we define k filter kernels. K can be any very large number. So, for instance, there are networks which define 512 such filters in every layer. Okay. And so, the output would be k feature maps of each of this particular size. So, typically in every layer each of the filter maps are of the same size, even though of each of this particular size. So, typically in every layer each of the filter maps are of the same size of each of this particular, and so you 512 very large find we can define many such filter kernels. So, we will define k filter kernels. K can be any very large number. So, for instance, there are networks which define 512 such filters in every layer. Okay, and so the output would be k feature maps of each of this particular size. So, typically in every layer, each of the filter maps are of the same size, even though there are exceptions which we will again look at later in later videos. So, typically you would also, for instance, you would one layer would contain, you would define 3 by 3 filters, about 256 of them. All filters would be of size 3 by 3. So, all the feature maps would be of the output feature maps would be of the same size, but there will be about k of them. Now, this another operation which we defined there was pooling. So, following convolution or a series of convolutions, there is also pooling. What does this pooling accomplish? One of the major advantages it gives, supposedly gives, is the translational invariance. So, you can, it is very easy to visualize. If you have an object in your picture and you are trying to localize it, let us say using the neural network. Now, if you keep subsampling the picture, let us say you subsample the picture from 256 cross 256 to 32 by 32, right, almost a factor of 8, 8 reduction, factor 8 reduction, okay, but almost exactly a factor of 8 reduction. So, let us say if the object moves around inside this image, inside the 256 by 256 image, if it moves less than 8 or 16 pixels, you will hardly see a motion in the 32 by 32 image. So, basically what this pooling performs is a subsampling operation. It reduces the size of your feature maps. And as you build more and more layers, comes to a point wherein very large motion of, so the network kind of becomes invariant to very large motion of the object you are trying to detect in your main image. Typically average pooling and max pooling are commonly used. We will look at max pooling, average pooling should be fairly obvious. So, let us say, let us take this feature map of size 4 by 4, this is of size 4 by 4, A typical max pooling operation would be it's again, you can think of it as using a kernel. So, you define a 2 by 2 kernel here, okay. And what max pooling does is to look at the maximum value inside this 2 by 2 space. Right. So, here it is 6, and the way max pooling is done, unlike we saw that for convolution you just slide the filter kernel by 1, here you slide the, you do not have overlap. So, you would slide so that there is no overlap. You can also skip, we will see that you can also stride and there is no overlap, and then in this window it is 8 is the maximum. Similarly, here is 3, in this window 3, and in this window 4 is the maximum. That is a typical max. So, we have it's so if you do max pooling of size 2 by 2, right, with a stride. In this case, the stride is how many pixels do you move before you do another max pooling operation. In this case, you move 2 pixels. So, the stride of 2 max pooling operation. In this case, the stride is how many pixels do you move before you do another max pooling operation. In this case, you move 2 pixels. So, the stride of 2, sorry, stride of 2, then you will half the size of the feature map. So, that is typically this is the function of the max pooling. So, if you want to be very systematic about it, you would try to retain the size of your feature map when doing convolutions. We will see how we can do that, and we will try to any subsampling will be done during the pooling operation. For average pooling, instead of the max value, you will take the mean of the values inside this 2 by 2 neighborhood. So, we saw that we mentioned earlier that the neural network, the volumetric convolutions or volume convolutions are done. Okay. So, what do we mean by that? So, because whatever we have seen so far, we are usually defining the filter kernels to be of just a 2 by 2 as a 2-dimensional matrix, right. So, for instance, we have a this is a 3 by 3 filter kernel, right. So, fx and fy. So, what do you mean by volumetric convolutions? How does it work? So, let us take this particular example, right. So, the input, let us just look at the input layer, it generalizes to all layers. So, the input layer is an RGB image, we have 3 channels. So, RGB, so input is input layer, so fx and fy. So, what do you mean by volumetric convolutions? How does it work? So, let us take this particular example, right. So, the input, let us just look at the input. We have 3 channels. So, RGB. So, input is 3 channels. Okay. So, basically our input size is nx times ny times 3. Okay. This 3 is each of them, the R, G and B, each of them is channel and each of them is an image. Now, when we perform a convolution, so let us say we define a 3 by 3 convolution. Okay, don't it need not be a 3 by 3, you can even do a 5 by 5 convolution just to prevent any if you are uncomfortable with 3 by 3, you can use a 5 by 5 kernel, it is easy to draw that. So, this is your filter. Let us say you are doing a 3 by 3 convolution on your input image which has 3 channels. Now, even though we say 3 by 3, the filter itself would be defined as three by 3 times 3. So, there will be a filter which operates on the red, green, blue, green and red. Each of them would be operated on by a 3 by 3 concurrently. Okay. So, a neuron in one of the output feature maps is the sum of all these outputs, right. So, we saw earlier all these outputs. Okay. So, a neuron in one of the output feature maps is the sum of all these outputs. right. So, we saw earlier, so when if we go back to the slides, back to the video, you see that we saw earlier that we superimpose the filter kernel on a region at a location in the image, multiply with the underlying pixel values to get one output. This is on a 2D feature map, a 2D input and one filter kernel. Now, we have in this case 3 channels. So, the filter kernel itself is 3 by 3 by 3. If we had 5 channels as input, then the filter kernel would be 3 by 3 times 5 with 45. Here it is 27 values, here it will be 45 values that we have tested, plus a bias unit if you want to include the bias. Okay. This is the this is how volumetric convolutions are done. The filter acts across the channels or across the volume. Okay. So, in this case the output, let us say we have defined k filters of size of a particular slice, then it will give you k feature maps. Okay. Now, if I do a 3 by 3 convolution, we are actually using a 3 by 3 times k type say k size filter to operate on this feature map. So, it will be 3 by 3, but it will act across the feature maps. So, this is what we refer to as volume convolutions, that it takes us the number of input channels can be variable. So, when you define, so typically you will you only define 3 by 3 or 5 by 5 filters, but it is implicit that those filters also act across the channels depending on how many channels you have. In the filter kernel will be unique kernel, let us say something of that sort, okay, right. So, you will have, so let us say if you have 3, if 3, this is the size determined by your backprop algorithm, okay. So, their weights will be estimated. Many beginners really falter here sometimes to understand this, okay. So, how do we determine the size of the output volume, okay, and what we have seen some hints so far, we will just do it very systematically. See, the size of the output volume or the feature map, it depends on the size of the input, we saw that, the size of the feature kernel, the filter kernel we are using, sorry, how much zero padding we do, we will see why we do zero padding, and the stride in our network, okay. So, padded convolutions, why would we want to do padded convolutions? So, we saw earlier that when we do a convolution with a, when we did a convolution with the 3 by 3 kernel, the output was less than the size of the input, okay. With the 3 by 3 kernel, the size of the output was less than the size of the input, okay. Suppose we want to preserve this size, the reason is if you have multiple convolution layers, as we do more and more convolution, at some point the feature maps, the size of the feature maps will become so small that you cannot do any more. Filtering, so that it actually acts as restriction on how deep you can go, okay. So, in order to avoid that, we sometimes would like to do padded convolutions. So, all we have to do is, so if you go back here, so this is our input feature map size. Again, we will just operate with one feature map at a time. It automatically applies to a volume, input volume. So, it is very difficult to show it on screen that way. So, we have a input image of size 3 by 3. It is very simple. So, if you apply this 3 by 3 kernel on this 3 by 3 image, your output will be 1 cross 1. That is typically what you get, but then you can't do subsequent filtering on top of that, it becomes difficult. So, to preserve the size of your feature map, so you will pad it with zeros all around. So, to preserve the size of your feature map, so you will pad it with zeros all around. So, So, to preserve the size of your feature map, so you will pad it with zeros all around. So, this corresponds to padding of 1, which means that you will pad with 1 on the left, right, top and bottom of the pitch. Your output, it is very similar to what we did earlier. You will position your filter kernel at the top left and then this by size 3 by 3. Okay. So, this is the idea behind padded convolution, is that it helps to preserve the size of your input. Of course, you can add more zeros too, it will be just be a slightly larger feature map you will get there, but you can add more zeros too, but typically it is done to preserve the size of your feature map, and the num0 padding is determined by the size of your feature kernel. So, in general, if you are we will just use square feature maps. As input. So, if your size of your feature map on one axis is n, okay, we saw that if you use a filter kernel of size f, then the size of the output is n minus f plus 1. Okay. So, if you have a padding of size p, in this case p equal to 1, n minus f plus 1, let us just write this more clearly. Right. So, output is n minus the size of feature kernel plus 1 and plus 2p. Okay. So, in this case our original n was 3, our filter kernel size was also 3 plus 1 plus padding is 1. So, 2 times 1. So, we will get 3 as output. Okay. So, if you want to preserve the size of a feature map following the convolution, then you would want 2p is f minus 1 or p is f minus 1 divided by 2, which is another reason why we would like our f to be odd. okay, then it's easier to, otherwise you will get some fractional values and you have to do round or floor and several adjustments have to be made downstream. You can work through that. So typically we will work with odd size filter kernels, 3 by 3, 5 by 5, 7 by 7. And so on and so forth, so that these calculations are simplified. Another operation that we typically do are strided convolutions. Again, we saw that with the convolution the size of the feature map reduces. However, it reduces gradually if you do, if you shift the feature map by 1 every time. Okay. So, the stride of 1 is typically what, by 1 pixel every time. The stride of 1 is typically what we do. However, if you have, let us say, a very large feature maps and we want to subsample it quickly, otherwise memory becomes an issue, then you do strided convolution. It is very simple, memory becomes an issue, then large feature maps and we want to subsample it quickly, otherwise memory becomes an issue, then you do strided convolution. It is very simple, strided convolutions are very simple to understand, except just that you skip a few pixels instead of moving the kernel on the image 1 pixel at a time, you would skip multiple pixels at a time, and how many ever pixels you skip is basically the stride you are using. So, stride 1 is what we saw earlier, is typically how we would go. But for stride, let us say 2, we saw that for, if let us say we want to do a convolution with stride of 2, then we saw we usually start from the top left right here, okay, and we saw we usually start from the top left right here, okay, and we just looked at, we skipped this, okay, just stride of 2. So, it moved 1 2 pixels and then you get the corresponding output there. Once again, as you go down, you will skip 1 2 and you will position the kernel there, and of course you would do one more skip to get there. So, your typically you should have obtained a 3 by 3 output, but because of the stride you will get a 2 by 2. Okay. So, the general formula for strided convolution, again giving the size of your feature maps is n, square n, you know that n minus f plus 2 p divided by the size of your stride plus 1. Okay. So, in this case it is very easy to verify your input was 5 as 5, feature map, the filter kernel size is 3, there is no padding, stride of 2 plus 1, you get 2, so 2 by 2 feature maps your output. So, you subsample very quickly typically. Okay. You will you typically work with odd sized odd numbers filter kernels, 3 by 3, not odd numbered filter kernels, sorry, the size of the filter kernels is pretty odd numbers. So, it is convenient to make these calculations, because you have to make sure that that at some point you do not run into these fractional values and it will be difficult to resize your feature maps at that. So, we typically work with this odd sized filters. Okay. So, to summarize briefly what we have looked at so far, they have a layer and a decision layer. Convolutions are based sequence of convolutions and max pooling layers leading to a fully connected layer and a decision layer. Convolutions are basically done by defining filter kernels at every layer in your network. So, every layer you will define k filter kernels, and the convolution is done by moving the filter kernel across the image and at every point multiplying with the underlying pixel values and adding to get the output. Max pooling is done to reduce the size of your feature maps. So, we repeat these layers eventually leading to a fully connected and a decision layer. So, we have not seen those yet. I have also not mentioned that there is a non-linearity there, of course, because this is a neural network. So, following a convolution you will usually do a pointwise non-linearity. So, what do I do by that, mean by that? Let us say for instance, so in this case I have done a convolution with a stride. I would take these values. So, this is what you would typically see in your ANN as a W transpose X, right, where in this case W is the elements of your filter kernel and the X comes from the pixel values here. So, you would pass it through a non-linearity like a ReLU for instance. So, every activation in the output feature map will be put through a non-linearity, that layer is always there. So, convolution followed by a non-linearity is typically done. That's a usual thing. So you have a, so if in the deep learning parlance, you would call it a linear layer, which is basically W transpose X, as we saw there. So you just sum of products and so on. So this is convolutional. Over the next few videos, look at a typical construction of a convolutional neural network. See what the layers are, how we define these layers, how we would define number of kernels in every layer and what it would look like, and how we would progress to, let us say, a fully connected layer and then to a distant layer, or can we skip the fully connected layers or not. That is another aspect that we would like to look at. So, that this we will cover in the next series of lectures. In this video, we will look at the different types of convolutions that are typically done in a convolutional neural network, and especially focus on the dilated and transpose convolutions, which are often used in deep networks and also in networks that have the encoder decoder type of architecture. So, just to recap, networks that have the encoder decoder type of architecture. So, just to recap, this is what we call naive convolutions. So, this is the typical convolutional operation that is done on a deep neural network. So, we have a given kernel size, we have a given kernel size k, stride used in the convolution and the padding, and given as input feature map of size I, IW and IS, high h, width and height. The output feature maps width and height are calculated by these formulas. So, it is the size of the feature map minus the size of the kernel plus 2 times the padding divided by the stride plus 1, that is the width. So, the typical same formula applies to the height also. So, this is the operation that we typically see. This involves superimposing the filter kernel, which is shown in red here, over the green input volumes, and then striding it across the input volume. So, just to illustrate, so if you go back, that is the first element calculated here by superimposing the 3 by 3 volume. And then once again we do the same by moving the filter kernel by one stride of, in this case the stride is actually 2, even though it is written as 1 here, it is actually 2 stride of 2, and we repeat this calculation throughout the cross section of the feature map. Now, dilated convolutions again are another convolution that are used to increase the receptive field of the convolution given the same given a smaller filter size. So, it is a cheap way of, cheap in the computational sense. Way of getting a larger receptive field using a smaller feature kernel, filter kernel. So, for instance, in this image we have this input feature map in green and the filter kernel is of size 5 by 5, and as we saw earlier we just move the filter kernel across the feature maps in order for us to obtain the output feature map shown here. Okay. Now, the idea is to use a 3 by 3 convolution with the dilation factor that can visualize the same area as a 5 by 5 convolution. while the number of parameters remain the same. That is, basically you have 9 parameters instead of the 25 parameters used in a 5 cross 5 convolutional kernel. However, by having a dilation in there, we can get the same receptive field size. So, how do we accomplish that? So, what is shown here in this image? Is that there is these red elements correspond to the elements of a 3 cross 3 feature map, and by incorporating appropriately rows and columns of zeros, we are making the size of the feature of the filter kernel 5 cross 5, and then proceed to do convolutions as before. Okay, so this is very advantageous in the sense that you will with little computational expense, you are able to get the same receptive field size. If we recall, as we seen earlier, in order to get a receptive field size of 7 cross 7, it is the same as doing 3 cross 3 convolutions in succession. So, that is an increased number of operations, while in this case we directly get a 5 cross 5 receptive field just by adding a appropriately adding zeros and 0 columns in the rows and columns of your filter kernel. The number of rows and number of 0 rows and 0 columns that you add is referred to as the dilation factor. Okay. So, just to recap, the idea is to inflate the size of your kernel by inserting rows and columns from zeros, so that you can get a slightly larger receptive field as the dilation factor. Okay. So, just to recap, the idea is to inflate the size of your kernel by inserting rows and columns from zeros, so that you can get a slightly larger receptive field. The next topic is the transpose convolution. Here the idea behind transpose convolution is to aid in increasing the size of the output feature map, and these are typically used in encoder decoder networks, especially on the decoder size, so as to increase the size of the feature map as you go towards the output. Okay. The idea is to regain the original spatial resolution. Not to regain the actual feature map itself, but just to have a just to regain the original resolution, that is the size of the feature map. And you have to appropriately pad with zeros and also insert zeros and zeros in rows and columns of your input feature map in order to obtain the appropriate sized output. Okay. The good way of thinking about it is to to see that is to how do the idea behind the transpose convolution is we interpret the input feature map. Let us say the input feature map is of size 2 cross 2, okay, and you have also been given a kernel size okay. Now we want to get a certain sized output, okay, it is given, let us say this is some m cross m. We do not do is we have to understand this, just that you assume that the input that you are given to the transpose convolution, this is the input to the transpose convolution, is an output of as a direct convolution. Okay. So, we have to find out what feature map size when operated upon with the kernel size of 3 cross 3, okay, given the padding and stride are given, will give this output size. Okay. And diluted convolutions, we try to regain that particular, we try to get that particular input resolution, which is basically trying to reverse that operation. Here once again to reiterate, we do not seek to get the input and in fact reconstruct the input feature map, but just to regain the resolution. The example given here, so you want to reconstruct this size, right, or you want to reconstruct this resolution, 5 cross 5 is your target output, and your input is actually a 2 cross 2 feature map given by these green squares. So, it is actually a 2 cross 2 input. Your filter kernel is of size 3 cross 3 given by this gray, okay, and you seek to obtain a 5 cross 5 output. Okay. Now, the stride parameters are given. So, if you think about it, the idea is what filters, what input feature size when convolved with a feature map with a filter kernel of size 3 by 3 would give rise to a 2 cross 2 output, right. So, that is what we would have to figure out. So, it turns out that this is 5 cross 5, and the idea is we, in order to regain this 5 cross 5 size, we have to actually have these zero padding on the outside. So, 0 padding of 2, and we also need to encoder-decoder networks, especially on the decoder size, so as to increase the size of the feature map as you go towards the output. Okay. The idea is to regain the original spatial resolution, not to regain the actual feature map itself, but just to have a just to regain the original resolution, that is the size of the feature map. And you have to appropriately pad with zeros, and also you would have to figure out is 3 cross 3. If you do a naive convolution, then you would get the output size would be 5 minus 3 plus 1. Which is 3 cross 3. Okay. So, which is not what we want. So, if you want to get a 2 cross 2 output, what do we have to do? So, let us say we have a stride of we add a stride of 2 in which case your output size would be two, 2 cross 2. Okay. So, if we have a slide of 2, no 0 padding, and we have an input feature map of size 5 cross 5, and your and your filter kernel is of size 3 cross 3, then with the slide of 2 your output feature map would be of size 2 cross 2. Okay. So, now we want to reverse this operation. So, since we have a stride of 2, we insert 1 or s minus 1, we insert 1 row of zeros and 1 column of zeros into the feature map of size 2 cross 2, right, and there was no 0 padding here. So, which means that we act, so the everything is reversed. So, that to understand this, so since there was no 0 padding here, we have to do a 0 padding when we do the transpose convolution, if you think of it that way. So, we have a padding of 2, right. So, in order to get the appropriate size feature map, and your slide is 1 as before. So, and your slide is again 1. So, if you do the convolution as like a naive convolution or your usual convolution with this particular input size, then you will end up with a 5 cross 5 feature map. Okay, so this transpose convolution is typically the one that is often used. Okay, so this transpose convolution is typically the one 5 feature map with this particular input size, then you will end up with a 5 cross 5 feature. Feature map. Okay, so this transpose convolution is typically the one that is often used in encoder decoder networks or in any situation where you have to upsample your feature maps. Another way of looking at it is that, let us say you have a network, right, and bunch of feature maps. This is a CNN, let us say, typically where this is your through the network input, then this during the backward pass or post matrix, right. So, the error you back propagate in this direction. So, as you notice, if you are back propagating the error from the smaller size feature map to a larger size feature map, which means here you are actually doing an operation which is same as the transposed convolution. Okay. That is the way of understanding transposed convolutions. Hello and welcome back. In this video, we will look at LeNet. So, LeNet 5 as it was called, dubbed, was first published, reported back in 1998. It was one of the earliest instances of convolutional neural networks used for image recognition. Its specific application was for digit recognition, and apparently had commercial application where it was used to read millions of checks in banks. So, this network serves as a kind of template for most of the modern networks that we see today. So, we will just briefly look at it and see some of the salient features of this network. So, this network took as input about 32 cross 32 images. This network was trained with images from the MNIST database. So, the images were around the size 28 by 28 and then these images were then further modified to, in fact, kind of like a data augmentation where several distortions were introduced and used for training this network. So, it took as input images of size 32 by 32. So, basically images of digits, handwritten digits, which has been discretized, scanned and discretized. So, the typical architecture is basically input followed by a convolution followed by a pooling layer, and this was repeated leading to a finally to a couple of fully connected layer, a convolution followed by a pooling layer, and this was repeated leading to a finally to a couple of fully connected layers and an out output, which is basically 1 of 10 classification. You have to classify 0 digits 0 to 9. Network had about 60,000 parameters. Okay, it has several interesting concepts here. For instance, the first layer had 5 by 5 convolution, no zero padding, which gives rise to a 28 cross 28 output. Followed by a 2, no zero padding, which gives rise to a 28 cross 28 output, followed by a 2 by 2 pooling. This is an average pooling operation. So, basically 2 by 2 average pooling with a stride of 2. So, the average pooling basically the output is basically 2 average pooling with a stride of 2. So, the average pooling basically the output is basically the average of the 4 elements in the 2 by 2 area of the filter, then followed by a 5 cross 5 convolution, again no padding, which gives rise to a 10 by 10 output, then subsequent which gives rise to a 16 cross 5 cross 5 maps. Now, when we do a 5 cross 5 convolution on top of these maps, it is basically the same as doing a fully connected layer, but then the paper actually just call this also calls this a convolution layer. This is also a convolution layer. So, we start with the 32 by 32 input here, perform 5 cross 5 convolutions followed by max pooling, and then one more 5 cross 5 convolution followed by a max pooling, okay, which gives rise to 5 cross 5 feature maps, 16 of them, and we do again 5 cross 5 convolutions on that, giving rise to 121 cross 1 outputs. That is the interesting part. The author also mentioned, Lakun is the first author of this paper, he mentions that this is what right now we call this as fully convolutional layers, right. So, if we have an input which is bigger than 32 cross 32, then the number of feature maps in this, the size of the feature maps in this layer would be higher than 1 cross 1. In fact, if you think about, let us say, a 64 cross 64 input, one way of looking at it is that we can slide the entire network across the 64 cross 64 with a stride of 32, and we can actually get a 2 cross 2 output here. So, if you can think about it that way. And then finally, a fully connected layer, and then to a decision layer or the output layer. You can use softmax here if you want. Okay. So, this has several things. Can use softmax here if you want. Fully connected layer, and then to a decision layer or the output layer.